In this video, we're going to continue our discussion on finding the derivative. Picking up where we left off, example C, we're going to find the derivative of f of x equals 7x plus 9. So once again, we're going to start by finding the difference quotient, so three-step process. First, evaluating our function at x plus h, we have 7 times x plus h in parentheses plus 9. And distributing the 7 through, we get 7x plus 7h plus 9. Step 2, we're going to subtract our original function from that, so don't forget to distribute the negative to the 7x and the 9 in the original function. And when we combine like terms, the 7x minus 7x is going to go away, and then the 9 minus 9 is going to go away, leaving us with just 7h. So step 3 is we're going to divide that result, 7h by h, and we get 7. So we're going to look at the limit as h approaches 0 of 7. Well, since there's no h to really evaluate, the 7 is going to be your limit. So our derivative of 7x plus 9 is 7. And notice that's also the slope of our line, and that's going to be true for any linear function. So non-vertical lines, the derivative is just going to be the slope. Again, that's non-vertical lines. All right, part D, we have f of x is x squared plus 3, so evaluating f of x plus h, when we substitute x plus h in parentheses and expand it out and combine it with the 3, we have x squared plus 2hx plus h squared, and then plus 3. Step 2, we're going to subtract our original function from that result, so we're going to distribute the negative to the x squared, distribute the negative to the 3, and our x squared minus x squared is going to go away. Our 3 minus 3 is going to go away, leaving us with just 2hx plus h squared. All right, step 3 is divide that result by h, and our difference quotient is 2x plus h. Now for the derivative, we're just going to evaluate 2x plus h as, take the limit as h approaches 0, which we can just use direct evaluation, and we get 2x plus 0, which is 2x. So our derivative of x squared plus 3 is 2x. Now the derivative has many other names it goes by, and oftentimes because there's various ways of describing something, it may make it more difficult when you hear it out of context in terms of something else. So for instance, when you, in your future studies, come across the phrase instant rate of change or instantaneous rate of change, that means derivative. So if you see that phrase or hear that phrase, think derivative. The tangent slope to a curve is also an interpretation of derivative. So tangent lines are lines that intersect a curve at one spot and only one spot. So tangent slope to a curve is finding the derivative of the function at that point. The limit as the secant line becomes the tangent line. So a secant line hits a function in 2 spots, and as the h value gets closer to 0, your difference in x coordinates gets closer to 0. So with your x coordinates getting closer and closer together, your line is getting closer and closer, only hitting the graph at one spot for where it's a tangent line, as opposed to 2 spots where it's a secant line. And fear not, because even though we looked at a very tedious way of finding the derivative, taking the difference quotient and looking at the limit as h approaches 0, when you do study calculus, you're going to learn a lot of shortcuts, so you won't have to do what we did in these notes to find the derivative. So for instance, let's take x squared plus 3. You'll learn shortcuts where, oh, it's just 2x. You won't even have to think about it. It'll be that instantaneous, pun intended, where you will see a function and be able to calculate the derivative with a lot more speed than we did in this video. But again, this was just an introduction to get you used to seeing stuff that hopefully won't be as intimidating now in your future as it might have been without these videos. So thanks for watching, and I hope you have a good one.